Now we're going to study fat points on the Fano scheme Fs. So we have two constructions that we have made so far. One of them was to understand that these fat points, or points over the dual numbers, tests non-reducedness or tangent directions of Fs. So if Fs is just a bunch of reduced points, then there should be no fat points. On the other hand, what we just did is to realize what points in Fs means. Those points in Fs will always capture some line inside of S. So even the meaning of points is a B point for some ring B, it then means a family of lines inside of S. So that connection was important because now instead of testing something rather algebraic, which was testing these fat points of Fs, which would mean studying the scheme generated by these polynomials Cj's, instead of studying those polynomials, I'm going to study the geometry of deforming a line, and by the discussion in the previous section, I will be able to solve my problem by the geometry of this question. Okay, so a family of lines over the dual numbers inside of S is something that we've almost studied because we considered lines over the dual numbers inside of P3, and we realized that they were lines with normal directions essentially. So we had a line, this is a line. A fattening of this line means I'm fattening every point on the line, every k point on the line I'm fattening. And remember there was an exercise that said that if you fatten a single point on a smooth variety, then you're actually choosing a tangent direction of that variety at that point. Now, the additional thing that we want is that this fat point has to lie inside of S. So the tangent direction that we're choosing is not only an arbitrary one on P3, but it should lie in S. And let's just draw a picture of the family of tangent directions that we're choosing. So the other thing to remember is that the Grassmannian was clever in that our tangent directions that we're choosing at each point should not be parallel to L. And it sort of makes sense out of this that it's actually looking at normal directions to L in some sense. It makes this canonical. So we're looking at normal directions to L, but these directions should lie inside of S. So one way to capture this idea is to say that we can construct the normal bundle to the line in S, and the infinitesimal deformation of the line should give me a global section of this normal bundle. So let's define this object, the normal bundle, right now. I begin with the tangent bundle to the line. So this is each point on the line together with a tangent direction. This is a line bundle on the line. So each point has one-dimensional space of tangent directions. And then I construct the tangent bundle to S. This is a vector bundle of rank 2. I pull back or restrict this vector bundle to L so that I have an inclusion from the tangent bundle of L to the tangent bundle of S. And the quotient by definition is called the normal bundle. The pictures that we are drawing suggests that any infinitesimal deformation of the line inside of S should give me a global section of this normal bundle. And what our pictures suggest, or the conclusions that we are drawing from them, are in fact correct. So there is something delicate here, but we've already studied this, that the Grassmannian was clever enough to ignore the tangent directions of the line itself. So if you were deforming points on the line along the line itself, then it would ignore this. And in fact, any deformation, even a normal deformation of the line, but somehow perturbed parallel to L, this will be killed. So we saw this very explicitly by playing around with the equations. That's why when I wrote down this exact sequence, you know that the kind of object that the Grassmannian sees is Ts over Tl. So it really sees this normal bundle. Now if we were to wrap up all of these observations, we say that any fat point of Fs based at a line L inside of S would have to correspond to a global section of the normal bundle NLS. So what we're seeing here is something fundamental to these moduli questions. In general, you could have asked, what is the tangent space of Fs? We saw that fat points, these k epsilon points, capture this tangent space of Fs. Therefore, what I just said in wrapping up this section is that the tangent space of Fs corresponds to the global sections of the normal bundle of L inside of S. But this is a much general phenomenon. And the general statement is this, that if you're trying to perturb a subvariety within some other larger variety, let's say in this case it's L inside of S, then first of all, its infinitesimal deformations correspond to the global sections of the normal bundle of the subvariety inside the larger ambient variety. But furthermore, if you have some moduli space parametrizing all possible embeddings of this subvariety inside the ambient space, then the tangent space corresponding to the particular embedding you have is, just as is the case here, is just the global sections of the normal bundle. It corresponds to the infinitesimal perturbations. So this kind of thing has much larger context, and we have our first exposure to it.